It all started when we were locked in a dark room, completely clueless on what's going on. We tried calling for help, but it was of no use. As we wandered around feeling completely lost and helpless, a screen suddenly lit up with a message from Anonymous.
Welcome, students, to your test of ingenuity and teamwork. You are trapped here, but the path to freedom lies ahead. To escape, you must conquer 2 challenges. First, design a robot capable of recognizing 7 images with precision. Think outside the box and collaborate to create something remarkable. Second, you must program this robot to achieve the fastest speed possible. Speed and accuracy are key to your success. Complete these challenges and the door will open.
After much discussion, we decided to split up into 4 teams.
Android team. So for the application, our team went with the cars team as we believe that we are speed.
We divided the Bluetooth functionality and the grid functionality into different activities to keep the app less cluttered. The app buttons are visually vibrant for easy distinction and recognition.
Users are able to plot obstacles by keying coordinates using the keyboard. This reduces the chance of missed clicks during the high-stakes competition. Although, if the coordinates are wrongly plotted, they can be either dragged to their correct positions or deleted off the map.
We have implemented the A-star search algorithm, and this is a technique which is used to path find between the 2 vertices, and this will return with the shortest path between the 2 vertices. This will help our robot to find the optimal algorithm and find the optimal path in return. The cost of each path will be pushed into a minimum heap, and together with that, the path with the lowest cost will be explored first. Along with that, the final computation of the shortest path, we will also display the time taken for it.
Furthermore, our simulator also demonstrates our algorithm by displaying the optimal path the robot has traveled while detecting obstacles. Some of our simulator features include allowing users to add extra obstacles for further testing and to clear all obstacles. As the simulator runs, the coordinates of the robot's current position and the command set will be printed in the terminal window.
Now for the STM and the hardware. To start, the robot will need to be able to move in a straight line. To achieve this, we take regular readings from the gyro and calculate the different motor speeds through a PID function. This way, the robot can self-correct any deviations from the straight path.
Following that, we programmed and calibrated the robot to execute turns in 4 directions. And to make the turns accurate as possible, we measure the motor speed and offset needed to keep every turn consistent.
And after executing every command, an acknowledgement will be sent back to the RPi. This way, it can collaborate with the other system.
The RPi is the brain of the robot and works as the middleman between the Android tablet and the STM. It needs to be able to receive the obstacle running on the flash server on a standalone laptop, receive the movement commands from the algo server, and then send them to the STM. Hence, we had to handle integration and communication between the various devices and ensure that the devices could connect to the RPi. We connected the Android tablet to the RPi wirelessly via Bluetooth and the RPi to the STM board via cable. For the communication between the devices, we mainly use JSON formatting for the input and output of the messages and commands.
For image recognition to detect the symbols in the images, we use a convolutional neural network model for computer vision. A YOLO V10 model is perfect for object detection as it is accurate, fast, and easy to set up. To ensure our model was able to recognize the images on different backgrounds, we trained it on a varied dataset of over 7,000 images. We also created our own images with custom backgrounds. And since the model is computationally intensive, we ran the CNN on the laptop running a flash server. The RPi sends images to the laptop's flash server, which processes the images and then sends the model results back to the RPi. Once the correct symbols are identified, the RPi updates the Android tablet with the correct code for task 1 and also enables our robot to navigate around obstacles for task 2.
After many weeks and late nights of integration and training, the day finally came. We managed to complete task 1, successfully detecting 7 out of 7 images within 1 minute 8 seconds, securing 3rd place on the leaderboard. For task 2, we were able to complete it within 30 seconds without hitting any walls or obstacles, reaching 5th place. And we were finally able to escape the room.